When people say terraform Mars, they usually mean something very specific. They mean making Mars behave like Earth on the surface. They want shirt-sleeve air pressure, liquid water that stays liquid, stable temperatures, and a breathable atmosphere that does not leak away. That sounds like an engineering project. But the reason Mars cannot be terraformed, at least not in any realistic sense, is that it is also a gravity project, a spacetime project, and a long-term cosmic evolution project. And gravity is not something we can manufacture at planetary scale, not with any technology that fits inside the known laws of physics and any energy budget that makes sense. Let me start with what we know about Mars and how we know it. We know Mars is smaller than Earth. We measure its mass from the orbits of spacecraft and its moons, and from how its gravity perturbs trajectories. We know its radius from imaging and laser altimetry. Once you know mass and radius, you know surface gravity. Mars gives you about 38% of Earth's gravity. That number is not a detail. It is the central constraint. Gravity sets the scale height of an atmosphere. It sets how tightly gases are bound. It shapes escape processes. It also affects whether a planet can keep internal heat long enough to drive plate tectonics and a long-lived magnetic dynamo. Those are not nice-to-have features. They are part of what keeps Earth's surface stable over geological time. We also know Mars has a thin atmosphere today, mostly carbon dioxide, with a surface pressure around 6 millibars on average. We know that from landers, from radio occultation, from spectroscopy. We know the isotopic ratios of noble gases and of hydrogen, and those ratios are like fingerprints of atmospheric loss. Heavier isotopes are left behind when lighter ones escape more easily. Mars shows that signature strongly. That is not speculation. It is measured chemistry that points to a history of escape to space. Now, if you want to terraform Mars, you need to solve 3 linked problems at once. You need enough atmosphere, you need the right composition, and you need it to stay there for a long time. People often talk as if you can just warm it up, release CO2 from the poles and the soil, and the rest will cascade. But the key question is not, can we add gas? The key question is, can Mars hold on to it? And that comes back to gravity, solar radiation, and the way space-time and energy flow govern particle escape. Atmospheric escape sounds like a simple idea. Molecules move fast. Some exceed escape velocity. They leave. But the real physics is richer. There is thermal escape, like genes escape, which depends on temperature and molecular mass. There is non-thermal escape, driven by photochemistry, by ion pickup, by sputtering from the solar wind. Mars is more exposed to those non-thermal processes because it lacks a strong global magnetic field today. We know that from magnetometers on orbiters. Mars has crustal magnetic patches like frozen remnants, but not an Earth-like magnetosphere that stands off the solar wind. That means the upper atmosphere interacts more directly with charged particles from the sun. Here is the thought experiment I use to keep this grounded. Imagine you succeed in making Mars warm and wet. You thicken the air. You get liquid water stable at the surface. Now ask what you just did to atmospheric loss. You raise the scale height by warming the atmosphere. You put more particles at higher altitudes where escape processes are stronger. You increased ultraviolet absorption because more gas means more targets for photons to ionize and dissociate. You may have improved shielding at some wavelengths, but you also created a bigger, puffier upper atmosphere. In other words, the very act of making it Earth-like can increase the rate at which Mars bleeds its new atmosphere away, unless you also solve the magnetic and gravitational constraints. On Earth, gravity is stronger and the planet is larger, so the same temperature gives fewer particles in the high tail of the velocity distribution relative to escape velocity. And Earth's magnetosphere changes how the solar wind couples to the upper atmosphere. It is not a perfect shield. Earth still loses atmosphere, but the loss is slow compared to the total reservoir. Mars is operating closer to the edge. Its escape velocity is lower. Its gravity well is shallower. That is not a moral judgment. It is just the geometry of space-time around a smaller mass. In Newtonian terms, less mass means less gravitational potential. In general relativity terms, the curvature is weaker. Either way, it is easier for particles to climb out. Could we just add an artificial magnetic field? People propose giant coils at Mars's L1 point, or rings around the planet. This is where I have to be strict about energy and scale. A magnetosphere is not just a static bubble. It is a dynamic system interacting with a variable solar wind. To create a field strong and large enough to stand off the solar wind at Mars, you need enormous currents and stable structures. Even if you could build it, you would need it to operate for thousands to millions of years if you want a stable biosphere, not just a temporary habitat. The engineering might be imaginable on paper, but the energy, materials, and maintenance burden is so extreme that it stops being terraforming and becomes building a planetary life support machine that never gets to turn off. That is a different category. Now let's talk about the atmosphere source problem, because it is often misunderstood. If you want Earth-like pressure, you need a lot of gas. Mars does not have a hidden ocean of nitrogen waiting to be released. CO2 is present in the polar caps and absorbed in regolith, but measurements and models suggest that even if you release the accessible CO2, you would not reach Earth-like pressures. You might get tens of millibars, or maybe more depending on assumptions, but not a stable 1-bar atmosphere. And composition matters. CO2 is not breathable. You would need oxygen, and oxygen is chemically reactive. On Earth, oxygen is maintained by biology over long time. Without a huge biosphere and a stable long-term cycle, oxygen will get consumed by rocks and reduced minerals. Mars has abundant iron-bearing minerals that will happily oxidize. So even if you somehow delivered oxygen, it would not just sit there. It would do chemistry. Water is similar. Mars has water ice. But stable surface oceans require pressure and temperature in the right range. They also require that water not be lost to space in the long run. Hydrogen escapes readily. We have direct evidence of ongoing loss today, including hydrogen in the upper atmosphere. If you warm Mars and increase water vapor, you increase photodissociation in the upper atmosphere. UV splits water into hydrogen and oxygen. Hydrogen escapes easily. Oxygen can escape too, or it can oxidize the surface. That is a one-way ratchet, unless you have a strong replenishment cycle. Earth's replenishment is tied to geology and biology. Mars does not have Earth's plate tectonics. Its internal heat budget is smaller. Its mantle cooled faster. That is again a gravity and size story. Smaller planets lose heat faster because of surface area to volume ratio. Cooling changes volcanism. Volcanism changes outgassing. Outgassing changes atmosphere. The whole chain is coupled. This is where I bring in dark matter and dark energy, not as decoration, but because they frame what kind of universe we are actually engineering inside. Dark matter dominates the mass budget of galaxies. It shapes the gravitational potential wells where galaxies form, and it sets the large-scale scaffolding of cosmic structure. But dark matter does not clump into planets. It passes through. It does not provide you with a hidden reservoir of extra gravity you can tap to deepen Mars' gravity well. In mainstream physics, dark matter interacts gravitationally and maybe weakly, but not in a way that lets you collect it and build a denser planet. So if someone says we'll add mass, the only mass available is normal matter. And adding enough normal mass to change Mars's gravity meaningfully is beyond absurd. To raise Mars's surface gravity close to Earth's, you would need to add a large fraction of Earth's mass. That is not moving a few asteroids. That is rearranging the solar system. Dark energy is even more important for the long view. Dark energy is the name we give to the observed accelerated expansion of the universe. We infer it from supernova distances, from the cosmic microwave background, and from large-scale structure statistics. It acts like a component with negative pressure in the equations of general relativity, leading to accelerated expansion on cosmic scales. It does not rip apart planets at present. It is negligible on the scale of the solar system. But it sets the fate of the universe, and therefore the timescales we care about. If the universe keeps accelerating, distant galaxies will recede beyond our horizon. The accessible resources for any far future civilization shrink in a very real physical sense. That matters because terraforming, if it were to be done in a robust way, is a multi-million-year commitment. You are not just making a place pleasant for a few centuries. You are trying to create a second Earth-like world that stays stable across stellar evolution timescales. In an accelerating universe, the long-term energy economy becomes tighter, not looser. Even before dark energy matters, the sun matters. The sun brightens slowly over time. Stellar evolution is well tested. We understand it from nuclear physics, helioseismology, and observations of other stars. Over the next billion years, the sun's luminosity increases. That shifts habitable zones outward. Mars is farther out, so in a distant future, it might sit closer to a comfortable temperature range. But that does not automatically give you an atmosphere, a magnetosphere, or a stable water cycle. Temperature is only one variable. And if you try to terraform Mars now, you are fighting both its present constraints and its future evolution. You might warm it into a more Earth-like state only to face runaway loss processes, and then, later, a brighter sun that pushes you toward instability again. Terraforming is not a single knob. Sometimes people propose using greenhouse gases like perfluorocarbons to warm Mars. The physics of greenhouse warming is real. We understand radiative transfer. We can model how different gases absorb infrared. But warming is not the same as terraforming. If you warm Mars without adding enough pressure, you still have near vacuum conditions. Water still boils or sublimates. Human physiology still fails. And if you add pressure with CO2, you create a toxic atmosphere with severe cold trap and condensation issues, and you still have to deal with loss to space. Also, producing industrial quantities of exotic greenhouse gases on Mars requires a huge energy infrastructure. Energy is not free. Solar power is weaker at Mars. Nuclear is possible, but now you are talking about a civilization-scale build-out, not a planetary conversion. Let's anchor this in the most unforgiving constraint: escape velocity and time. Mars can hold heavy gases better than light ones, but it is still vulnerable. Nitrogen is heavy enough to stay better than hydrogen, but nitrogen is scarce. Oxygen is reactive. Argon is inert but not biologically useful. CO2 can be retained better, but it condenses, and it is not breathable. And all of these are affected by upper atmosphere heating from solar UV and by sputtering. Measurements from missions like MAVEN show that atmospheric escape has been significant over Mars' history. That is part of why ancient Mars could have had thicker air and liquid water, yet ended up cold and thin. The planet did not just choose to dry out. It followed the coupled evolution of gravity, interior cooling, magnetic field decay, and solar forcing. So when I say Mars cannot be terraformed, I mean that Mars cannot be made into an Earth-like, self-sustaining, open-air biosphere with plausible interventions that do not require continuous, indefinite civilization-scale maintenance. You can build habitats. You can build domes. You can build underground cities. You can even imagine regional atmospheric engineering, like enclosed valleys or pressurized canyons. Those are hard, but not physically impossible. But that is not terraforming in the classic sense. Classic terraforming implies you can step outside and the planet itself provides life support. For Mars, the planet does not want to do that because its gravity well is shallow, its protective magnetic environment is weak, and its volatile inventory is limited. And the deeper point is that these are not isolated engineering challenges.